All right, let's talk about database normalization. If you've ever wrangled with data, you've definitely heard this term thrown around. It sounds kind of complex, maybe even a little scary, but honestly, it's one of the most important skills you can have for building clean, efficient, and trustworthy databases. So let's just dive in and pull back the curtain on this thing together. But before we get into the how, let's talk about the why. Why should you even care? Well, think about a giant messy spreadsheet. You know the one, where the same customer's name is spelled 3 different ways, or you update an address in one spot, but it stays the same in 10 others. It's not just annoying, it's a recipe for disaster. It leads to real-world errors, completely wrong reports, and just a ton of wasted time. That's the kind of chaos we're here to clean up.
So, here's our game plan. First, we're going to identify the main villain, the redundancy problem. Then, we'll conquer it step by step, climbing the ladder of normal forms. First, second, third, and the super strict Boyce-Codd. And finally, we'll zoom out and talk about the real-world trade-offs you have to make.
Every good story needs a villain, right? And in the world of database design, the big bad guy is, without a doubt, data redundancy. This is the core enemy that normalization was invented to defeat.
Now, you might hear redundancy and just think, oh, so it wastes a little disk space, no big deal. But the real danger is way, way worse than that. It creates these things called anomalies, which is just a fancy term for really nasty errors that pop up when you try to update, add, or delete your data. I mean, think about it. If you have the same bit of info in 10 different places and you miss updating just one of them, boom. Your data is now inconsistent, unreliable, it's basically lying to you.
So what's the technical culprit behind all this mess? It's something called a functional dependency. All that means is there's a rule in your data that says if you know column A, you automatically know column B. For example, if I know your employee ID, I know your name. Simple. But here's the catch. Not all of these rules are bad. The trivial ones are totally fine. It's these non-trivial ones that are the real troublemakers we're hunting down.
And this right here, this is our hit list. These are the 3 specific types of dependencies that cause all that redundancy. We'll call them case I, case 2, and case 3. Each normal form we're about to cover is like a specialized weapon designed to take out one of these guys. We're going to defeat them one by one, starting right now.
Okay, first up. First normal form, or 1NF. This is ground zero. It's the absolute foundation that everything else is going to be built on. And the rule for 1NF is beautifully simple. Your data just has to be atomic. It sounds all scientific, but it just means this. One cell, one value. That's it. You can't have a list of phone numbers crammed into a single cell. You can't have a full address, street, city, state, all jammed together in one box. Nope. One cell, one single piece of information. That's the whole rule.
Now, the good news is, if you're using any modern relational database, it pretty much forces you to do this anyway. So you're probably in 1NF without even trying. But, and this is a huge but, don't start celebrating just yet. 1NF is a great start, but the level of redundancy is still through the roof. We've poured the foundation, but our house is still a total mess.
All right, foundation set. Time to move up to the next level and tackle our first major source of that redundancy. Let's talk about second normal form.
Remember our hit list? We are now officially targeting case I. This problem happens when your main key is made of multiple columns. We call that a composite key. The issue arises when another column in your table depends on only part of that key, not the whole shebang. This is the exact problem that 2NF is designed to fix.
The official term for this is a partial dependency, and it's pretty self-explanatory. An attribute is only partially dependent on the full key. So let's say your key is student ID, course ID. Does the student's name depend on both of those things? Of course not. The student's name only depends on their ID. It doesn't magically change because they signed up for a different class. That is a classic partial dependency.
And the solution is, you guessed it, second normal form. The rule is simple. To be in 2NF, a table has to be in 1NF, and it absolutely cannot have any of those partial dependencies we just talked about. By knocking out case I, we've just taken a huge swing at our redundancy problem.
We are on a roll, so let's keep going and tackle a sneakier kind of redundancy. It's time to level up to third normal form.
Okay, back to our map. Our next target is case 2. Now this one is a bit different because the dependency doesn't even involve the main key. Instead, it's when one regular non-key column determines another non-key column. It's this indirect chain reaction that causes all kinds of headaches.
This is called a transitive dependency. The best way to think of it is like dominoes falling. The main key, A, knocks over another column B, like a department ID. Then that department ID, B, knocks over yet another column C, like the department's physical location. See the problem? The location doesn't depend on the main key directly, it depends on that middleman column. That's a transitive dependency.
So 3NF steps in to clean this up with a very specific rule. For any dependency you find where X determines Y, one of two things must be true. Either the thing on the left, X, is a superkey, which basically means it can uniquely identify a row, or the thing on the right, Y, is part of a primary key. As long as one of those conditions is met, you're good. No more sneaky, indirect dependencies. We've defeated partial dependencies and transitive dependencies. We're so close to perfect, clean data. But there's one final, even stricter form to get us there. Boyce-Codd Normal Form, or BCNF.
Okay, this is it, our final target, case 3. Now this is the most complex one, and it usually only pops up in tables that have multiple, overlapping potential keys. This is when a part of one possible key ends up determining a part of another possible key. BCNF is the specialist we call in for this very specific, very tricky situation.
So what's the big difference between BCNF and 3NF? It's actually super simple when you see it side by side. Remember how 3NF had 2 escape clauses? A dependency was okay if X was a superkey or if Y was part of the key. Well, BCNF looks at that second option and says, nope, not good enough. BCNF is stricter. It has only one condition. For any and every dependency, X must be a superkey, no exceptions. End of story.
So we've climbed the entire ladder, all the way from 1NF to the peak of BCNF. But here's the real-world question. Is higher always better? Let's zoom out and put it all together by looking at the trade-offs.
This table sums up our whole journey perfectly. As you move from left to right, you can see redundancy dropping until you hit 0 with BCNF. Awesome. All of them guarantee a lossless join, meaning you can split tables apart and put them back together without losing any data. Critically important. But look at that last row. BCNF, in its quest for absolute purity, sometimes has a casualty. It might not be dependency preserving. Sometimes to enforce that super strict rule, you might break one of the functional dependencies you need, which can make your life harder later.
And that really gets to the heart of it. Normalization isn't some academic test where you have to get to the highest level to win. It's a practical tool. Honestly, most database designers aim for 3NF as the sweet spot. It gets rid of all the most common problems while making sure you preserve all your data rules. BCNF is great, but you have to be aware of what you might be giving up to get there.
So I'll leave you with this final thought to chew on. We've spent all this time trying to eliminate redundancy. But if pushing for higher normal forms means splitting your data into tons of different tables, making it slower and more complex to get the answers you need, when might it be a smart move to intentionally break the rules and choose a lower normal form? That's when database design stops being a science and starts becoming an art. Thanks for watching.